This video is on section 6.5 notes, product and sum identities. So this video is talking about some different identities that, to be honest, I don't think we'll work with very much. But these identities connect some product, so things that are multiplied, with some of the sum and difference identities, and it just kind of makes a connection between the two that's a little bit different than just the standard sum formula. So first we're going to look at the product to sum, so starting with a product, turning them into a sum, and then we'll do vice versa. So as we evaluate these, we're going to do two things. We're going to rewrite some of them, and these are going to be with values that do not show up on the unit circle. And then we'll look at some where we can find the exact value, and that's if when we rewrite them, we end up with values that are on the unit circle, then we'll be able to find the exact value. So for this one, we're just going to rewrite it. We're going to start with the product. We have sine of a degree measure times cos of a degree measure, and that fits the very first formula. So I'm going to write 1/2 times sine of the first angle plus the second angle, so 12 degrees plus 9 degrees, plus sine of the first angle minus the second angle, and all I have to do is actually add those two angles together. So 12 plus 9 is 21, and sine of 3, I guess I didn't need those extra parentheses, but there it is. So half of sine 21 plus sine 3. That's it. For the next one, sine of pi 12ths times sine of pi 8ths. We're going to look at the one that has sine times sine. So I've got 1/2 of cos, the first angle minus the second, pi 12ths minus pi 8ths, minus cos, the first angle plus the second, pi 12ths plus pi 8ths. This requires a little bit more fraction fluency than I have off the top of my head, so I'm going to go ahead and use a calculator. So 1/12 minus 1/8 is negative 1/24, so negative pi 24ths, 1/12 plus 1/8, 5/24ths, and for cos of a negative angle, we can use our even and odd identities here. And if you have cos of a negative angle, that's just cos of the angle. So I'm going to have 1/2 cos pi over 24 minus cos 5 pi over 24. There we go. That's as simple as we can get it, unless we were to use a calculator to get decimals. Next, it says find the exact value of the following. So I'm going to do it the same as the previous problems, but I'll be able to use my unit circle to help me evaluate. So I have cos times sine, so I'm going to be using the third formula down. So I'll have 1/2 sine 67.5 plus 112.5 minus sine 67.5 minus 112.5. So this is sine, I don't need these parentheses, sine of 180 degrees, definitely on the unit circle, okay, minus sine, nope, that was positive, negative 45 degrees. Okay, sine of 180 degrees is just 0. Sine of negative 45, we know you just take the negative away from here and it's negative sine of 45. Negative sine of positive 45 degrees. And so 2 minuses in a row make a plus. So I've got 1/2 times 0 plus sine of 45 is root 2 over 2. So I have 1/2 times root 2 over 2. And so that's going to give me root 2 over 4. All right, on to the next page. Very similar, but we have sum to product identities. And so we'll look at some sums, and then we're going to rewrite them as products. So same thing, we have some that just say rewrite, and then we have some that say find the exact value. So for this one, we're going to rewrite it. We have sine plus sine, so that matches the first formula. So that gives us 2 times sine of the first angle plus the second angle divided by 2 times cos of the first angle minus the second angle divided by 2. So that's 14 over 2. That's 2 over 2. So that gives us 2 sine of 7 degrees cos of 1 degree. We can do the same thing down here. So cos minus cos, that's going to be this last formula. So we have negative 2 times sine of, we're going to add the angles together, over 2 sine, and we're going to subtract the angles. (13 pi 40ths over 2). (3 pi 40ths). And I guess I probably should have just done it all at once, but we're taking those fractions and we're dividing them in half, dividing them by 2, so that would be 13 pi 80ths, and then sine of 3 pi 80ths. And you can put the parentheses around the angle, but you technically don't need to. And that's what we would have for the second problem. For the last one, we have cos plus cos, and so that's the third formula here. So we're going to do 2 times cos, angle plus angle divided by 2. And then cos times the angle minus the angle divided by 2. So for the first one, that's 180 degrees divided by 2. And 45 degrees divided by 2. Okay, cos of 90 is 0, and we're lucky for that because 2 times 0 times cos of 22.5, whatever that number is, it's going to make the entire thing evaluate to 0. If this had been any other number, then we would have had to do a half angle identity for this one. So if that hadn't been 0, then we would have been getting out our half-angle identities, we would have been doing that formula, and then this third piece to evaluate using the unit circle to find the exact value of this third piece would have been a little bit more complicated. However, we know that because of that cos 90, the whole thing is just going to be 0. Okay. Next, we're going to learn something called the reduction formula. And the reduction formula is a way to write equations by kind of reducing them down into a more simple equation. So it says if alpha is an angle in standard position, and remember standard position means that you start drawing the angle at the positive x-axis. It's the way that angles are measured on the unit circle, where you've got 0 and then 90 degrees is the top of the positive y-axis. You've got 45 degrees in quadrant 1, you've got 135 in quadrant 2. You know, the way that you typically would measure those angles, that's from standard position. The terminal side contains the point AB. Then a times sine x plus b times cos x, so you notice that this is an equation like in terms of sine and cos, we haven't really seen those before, equals the square root of a squared plus b squared times sine of x plus a, or plus alpha, for any real number x. Okay, so we're imagining that these are two equations that you would be graphing. So you're thinking you have like y equals negative 3 sine x minus 3 cos x, and you're going to rewrite it as y equals a times sine of x minus c. So you're taking a formula like this with sines and cosines that we wouldn't really know how to graph, and we're rewriting it as a sine curve with some sort of amplitude and some sort of phase shift, something that we would know how to graph. And so this reduction formula is actually kind of nice to work with. Okay, so what I'm going to do first is I'm going to figure out what the A and the B value are, and I'm going to kind of draw a picture because it says alpha is from that standard position. So this is kind of referring back to all these different things that I know that I've worked with over the past couple units. So I know that my A value right here, A is negative 3, B is also negative 3. So if I go left 3 and down 3, negative 3, then I can kind of think of this as like a triangle right here where I went like left 3, down 3. And then I'll think of my angle from standard position being this angle that is drawn around that way, like that. Okay, and then I'm going to go ahead and I'm just going to do the square root of a squared plus b squared. You might recognize that's your Pythagorean theorem right there. That's going to help you find this hypotenuse. So the square root of a squared plus b squared is the square root of 9 plus 9. So this is the square root of 18, square root of 9 plus 9. And that's a square root that can be reduced. 18 is the square root of 9 times the square root of 2, which is 3 times the square root of 2. So for this triangle that I drew, the hypotenuse is 3 times the square root of 2. 3 times the square root of 2. And if you remember, whenever we draw these right triangles, the hypotenuse is always positive. So the part that's left and right could be negative, and this one happens to be negative because we're going to the left. The part that's up and down can be positive or negative. This one happens to be negative because it's going down. But the hypotenuse, whenever we draw that in, that value is always going to be positive. All right, so now I'm going to go ahead and I'm going to find the angle alpha that they're talking about. And I'll go ahead and just say sine of alpha is opposite over hypotenuse. It's a good way to figure out just what angle exactly that we're talking about here. So negative 3 over hypotenuse is 3 square root 2. These 3's cancel. So I have negative 1 over square root 2, and you might recognize this, you might not recognize it yet. this is not proper. I would need to rationalize this. So I'm going to go ahead and I'm going to multiply by root 2 on the top and root 2 on the bottom. And I get negative square root of 2 over 2. So at this point, we should recognize this. We're saying, oh, sine of some angle equals negative root 2 over 2. Well, that's on the unit circle. And so now I just have to think about, if my picture is drawn in quadrant 3, what is the alpha in quadrant 3 that has sine equals negative root 2 over 2? So in quadrant 3, alpha is what that makes the y-coordinate negative root 2 over 2? And the answer is, it is 5 pi fourths. Okay, so once you solve for this, that is the alpha is the angle in standard position, okay, whose terminal side is AB. And this is AB, it's negative 3, and we got that from A and B from right here. Okay, so alpha is that, and then alpha shows up in the formula right here. Okay, so we're rewriting the equation from this over to this, and it started off as this, and now we're going to write it as the square root of a squared plus b squared, which we know simplified to 3 square root 2, times sine of x plus alpha, and alpha is 5 pi fourths. Now, this seems insane, but if I were to graph these are identical. So I'm going to go ahead and show you, because this is a great way to check your answer and make sure you got it right. So I'm going to go over here to my window first, because our sine graphs and our cosine graphs typically have specific windows. So left and right, x min, x max, I'm going to type in negative 2 pi and positive 2 pi. And then normally the graphs bounce between negative 1 and positive 1, but this graph has an amplitude of 3 times the square root of 2. So I'm going to do like 5, 6 maybe. I'm going to do negative 6 to 6. I just want this to be big enough that I can see the whole curve, okay? So I did left 2 pi, right 2 pi, down 6, up 6. This is just telling me that it's going to put a scale of 1, so it's going to put a little slash every box. Maybe I should switch this to like pi halves or something. This makes sense though. Putting a little divot for every one box makes sense. And then here I switched it so that it would put a little marker at every pi halves. Okay, now if I go to y equals, what I'm going to do is I'm going to graph this one first. Negative 3 times sine x, negative 3 times cos x, negative 3 sine x, minus 3 cos x, and I am in radians, okay. Negative 3 times sine x, negative 3 cos x, I'm just going to let that graph, and so here is my graph. And then if I did this problem correctly, I'll be able to graph this equation next, but this will not change because it will just be graphing the second equation on top of the first. It will be identical to the first. If I did something wrong, I'll see a second curve somewhere else that is not the same. So 3 square root 2 sine x plus 5 pi fourths graph. And I don't see anything different because it's just graphing the second equation. And actually it's still graphing. There we go. So the first equation is graphed, the second equation is graphed, and they look identical. This is a little bit nicer to do if you do it on Desmos because you can actually see the 2 different colors. But I just confirmed that my answer is correct. All right, let's go ahead and try another one of these using the reduction formula, now that we know how to do it. So we're going to rewrite negative 2 sine x plus 2 cos x into this transformed sine curve. So I'm going to start off. Here's my A value. Here's my B value. So I'm going to go left 2, up 2 to draw my triangle. Left 2, up 2. Left 2, up 2. Okay, there's my triangle. And so I'm in quadrant 2, and I'm going to go ahead and do my Pythagorean theorem. Negative 2 squared plus 2 squared. That is 4 plus 4. This is the square root of 8. And so if I reduce that, I have square root 4 times square root 2 is 2 square roots of 2. Okay, so that's the hypotenuse of my triangle, 2 square roots of 2. Okay, so now I can go over and I can say sine of alpha is opposite, which is 2 over hypotenuse, which is 2 square root 2. And I chose sine for both of these, but in theory you could use cos or you could use tan to find the alpha, because the alpha is the same no matter which function you're using. So I'm just using sine, but you could use another one. The 2's cancel. I get 1 over root 2. And just like I did on the previous problem, I'm going to rationalize this. And I end up getting root 2 over 2. So I'm looking for which alpha, which angle, gives me sine or gives me a y coordinate of root 2 over 2. And this alpha needs to specifically be in the second quadrant. So in quadrant 2, alpha is 3 pi fourths. That's the value that gives me a y coordinate of root 2 over 2. And so now I have enough information that I can write my equation. Y equals 2 root 2 times sine of x plus 3 pi fourths. And if I want to check my answer, I can graph this as the first equation, I can graph this as the second equation, and I can make sure that they look identical on the graph, that they graph as the exact same curve. Okay, so next, that's what we're going to do. It says, it gives you this curve right here and says graph one cycle of the function. Well, I don't know how to graph this. It's got a sine, it's got a cos. We didn't learn any shortcut for how to graph sines and coses. But if I use the reduction formula and rewrite it as a transformed sine curve, I do know how to graph a sine curve, and then I'll be able to do it. So that's what I'm going to do. I'm going to start here with my a value, and then in front of cos that would be a 1. So there's my b value. So right square root 3 up 1. Okay, I'm going to go ahead and do my Pythagorean theorem. So square root of 3 squared plus 1 squared. Square root of 3 squared is 3. 1 squared is 1. 3 plus 1 is 4. And the square root of 4 is 2. So the hypotenuse is 2. Thank goodness. This one's going to be a little bit easier, especially since we have to actually draw it. And then over here, I'm going to find my alpha. I'm going to say sine alpha is opposite over hypotenuse. So I'm going to say where in quadrant 1 is the y coordinate 1/2. And in quadrant 1, alpha is pi over 6 when the y coordinate is 1/2. And so that means the equation that we're going to graph is 2 sine of x plus pi over 6. Okay, so if I need to state the amplitude, the period, and the phase shift, I'm going to say the amplitude is 2. The x is all by itself, so I know the period of the graph is just 2 pi like normal. And the phase shift is negative pi over 6 or left pi over 6. Okay, so I can go ahead and draw my axes. It's okay. And I know that normally I do sets of 4 for the period of the graph. I do sets of 4 or 8 or 12. And since the period is 2 pi, but I have to move left pi over 6, I'm going to do 2, 4, 6, 8, 10, 12 for 2 pi, because that will let me do 6 for pi, which will be easy to do 1/6 to the left and right. So 2, 4, 6, there's a pi. 2, 4, 6, there's a 2 pi. 2, 4, 6, there's pi. 2, 4, 6, 2 pi. 2, 4, 6, 3 pi. Okay, so just like normal, I'm going to start off with my sine function with a period of 2 pi and an amplitude of 2. So start at 0, end 0, 0 in the middle, go up to an amplitude of 2, go down to an amplitude of 2. And then I do have to do the phase shift. I have to shift this to the left pi over 6, which is 1 box, because I had 6 boxes as a full pi. So there is my curve. And again, if you wanted to check it on Desmos or on your graphing calculator, you could. Okay, so if a times sine x plus b times cos x is identical to y equals the square root of a squared plus b squared times sine of x plus alpha, if they're the same, then this curve is just a sine curve with transformations. Then that means that this curve, the curve with the transformations, has an amplitude of the square root of a squared plus b squared. It has a period of 2 pi. The period would always be 2 pi because the x is alone. There's no b value in the front of it to change the period. And it has a phase shift of left alpha. It has a phase shift of negative alpha or left alpha. And so then we would always be able to answer questions about the amplitude, the period, and the phase shift just from the formula. All right, last page. Okay, so this first part is actually from section 5.2. We just skipped it at the time. And then what they're doing now is they're circling back in this section. So we're just going to do it all here. And to be honest, there's not a lot of problems on this, so it might hopefully make more sense for us to do it all together. So it says, consider a spring in equilibrium position. So that's 0 right here on a vertical number line, as shown to the left. The weight on the spring is at rest, meaning it's not moving. If the weight is set in motion with an initial velocity of v sub 0 from a location x sub 0, then its location at the time is given by this equation. And you can recognize this is kind of like what we were just talking about, where you have a sine portion plus a cos portion. The letter omega, this kind of looks like W, is a Greek letter. It's a constant, which means it's not a variable. It's not going to be changing. It's a specific number that depends on the stiffness of the spring and the amount of the weight that is on the spring. For positive values of x, the weight is below equilibrium. So you can see that the number line is a little bit backwards, where if it goes up, it's negative, and if it goes down, it's positive. And so you'll notice that in the description, it's a little bit backwards. So it says for positive values of x, the weight is below equilibrium, and for negative values, it is above equilibrium. The initial velocity is considered to be positive if it is in a downward direction, and negative if it is in an upward direction. So for the first problem, it says a weight on a certain spring is set in motion with an upward velocity of 3 centimeters per second. So in a position 2 centimeters below equilibrium. So upward velocity, upward direction is negative. So the velocity is -3, and a position 2 centimeters below equilibrium. And this also was kind of the opposite of what we would think. And so below equilibrium was positive values. That's a +2. Assume that for this spring and weight combination, the constant omega has a value of 1. Write a formula that gives the location of the weight in centimeters as a function of the time t in seconds, and find the location of the weight 2 seconds after the weight is set in motion. So 2 seconds would be when the time is 2 seconds, okay? And you can see up here that this equation is x equals instead of y equals, and it's written in terms of the variable t. So you plug in t, you spit out an x. Okay, so we just have to plug in these values. We get x equals -3 over omega was 1 sine of omega times t plus x sub 0, so that's 2 cos of omega times t. Okay, so our equation, if we just kind of clean this up here, we get x equals -3 sine of t plus 2 cos of t. Okay, so that looks really similar to the equations we were just working with. So that's the answer to the first part of the question. It said write a formula, so we wrote a formula. And then it says find the location of the weight 2 seconds after the weight is set in motion. So take the equation, plug in 2, and see what you get. -3 times sine of 2 plus 2 times cos of 2. And so in here, we're going to type 2 in. Now, one thing that I've said to you guys is that whenever you actually hit the sine and the cos buttons on your calculator, then it matters what mode you're in. It matters if you're in radians, it matters if you're in degrees. And in here, in this problem, in the context of this problem, it doesn't really tell you based on the context whether you should be in radians or degrees. And so the best thing I can say to you is that typically in upper level math, in calculus and pre-calculus, the default tends to be radians. So unless you know for certain you should be using something else, use radians. Okay, so I'm going to make sure my calculator's in radians, and then I'm going to go ahead and just type this in. And I get -3.6 as the location, and so negative is kind of like the opposite of what I would think, right? Negative is this way, so that means that this is above equilibrium. I am 3.6 centimeters above equilibrium, or the weight is 3.6 centimeters above equilibrium after 2 seconds. All right, down here it says the same equation is used for a weight attached to a horizontal spring and set in motion on a frictionless surface as shown to the right. The reduction formula can be used on the spring equation to determine how far a spring actually stretches and compresses when the block is set in motion with a particular velocity. Okay, so we're going to be doing, working with the same type of equation, and this time we're going to be using the reduction formula. So it says at time t equals 0, the 1 kilogram block is moved and the spring is compressed to a position 1 meter to the left of resting position. And this one is a little bit nicer because the negatives are on the left like we would expect, the positives are on the right like we would expect, and so things are not backwards the way they were in the previous problem. So when it's to the left of resting, that means that this starting position is actually, -1. From this position, the block is given a velocity of 2 meters per second to the right, which means it's positive. Okay, velocity of 2 meters per second. Velocity is 2. Okay. We're going to use the reduction formula to find the maximum distance reached by the block from rest, and we're going to assume that omega is 1. So I'm going to use the same formula. So I've got the velocity, the starting velocity divided by omega times sine of omega times t minus, plus the x sub 0 value, so it was plus -1 times cos of omega times t. And so that means my formula is 2 times sine of t minus 1, or just minus cos of t. There's my formula. And so if I use the reduction formula now, I guess I'll put the 1 in there, that could be helpful. Then that means that my a value is 2 and my b value is -1. Okay, so I'm going to think of my little picture here. Right 2, down 1. So I'm in quadrant 4. To the right 2, down 1. And I'm going to do my Pythagorean theorem. 2 squared plus -1 squared. 4 plus 1 is 5, so this is the square root of 5, and so that's my hypotenuse. All right, so to picture the actual numbers that we have going on here, we have this formula, right? We chose those numbers to plug in and to be represented here, and we know that we could write a sine curve with transformations that could represent this exactly right here, and this curve, this sine curve, represents the movement of the spring. So if you can imagine, the spring at rest could kind of be like the midline of the curve. This is how I picture it, is that the midline of the curve is like the spring at rest. Then the amplitude of that curve talks about that maximum distance that is reached by the block from rest. And so the maximum distance that's going to be reached is the amplitude of this curve. And we just found it. It's the square root of a squared plus b squared. So this is the maximum distance. It is the amplitude of the curve. And you can find that by using the reduction formula and doing the square root of a squared plus b squared.